Okay, so in this problem, we're looking at a compound manometer, and what we end up having is a pipe A and a pipe B. Pipe A flows water upwards, and pipe B flows water downwards. And we have the compound manometer in between those two pipes. So what we end up doing here is we fill the compound manometer before we end up flowing water through those pipes with mercury on the left and right and oil between those two runs of mercury. And as we begin to flow water through A and B, the static pressure of the water in both A and B ends up filling up these evacuated sections with water. And these levels, A, B, C, and D, end up going up or down depending on what the static equilibrium condition of the compound manometer is. So as the pressure delta between A and B changes, the levels A, B, C, and D will end up changing correspondingly. A static equilibrium condition is reached, and based on those levels A, B, C, and D, we could determine what the pressure delta between the water in pipes A and B actually is. So in this problem, as we flow water through A and B, our manometer has reached a static equilibrium condition consisting of A, B, C, and D with heights H1, H2, H3, H4, and H5. And our goal here is, as we mentioned, to find the difference in static pressure between the internal flow at A and the internal flow at B. So finding the static pressure difference between the water in A at this location and the water in B at this location. So before we start, we're going to recognize that this is a hydrostatics problem in which we're going to apply the hydrostatic pressure equation. So we're going to take Z as positive upwards, parallel but opposite to gravity, which is downwards. So our assumptions are as follows. One, we're going to neglect surface tension. So any of the meniscuses that form at D, C, B, or A are going to be neglected. We're going to assume, two, that we're in static equilibrium. Three, we're going to assume that gravity is the only body force, so we can actually use the hydrostatic pressure equation. Four, we're going to assume that our flow in our system is isothermal, incompressible, and that we have a constant magnitude of gravitational acceleration, so we can use the simplified version of the hydrostatic pressure equation. And five, we're going to assume that the diagram as drawn on the left here is not necessarily to scale. Okay, and then we have our water in blue, our mercury in yellow, our oil in pink, and we have our magnitude of gravitational acceleration, which we're going to take as lunar gravity. We're going to assume that this compound manometer is actually on the moon. And we have our heights listed here. So H1 is 8 inches, H2 is 2 inches, H3 is 5 inches, H4 is 6 inches, and H5 is 7 inches. Okay, and we also have our specific gravities listed here. So let's begin with the first step of this problem. The first step of this problem is recognizing that we're going to use the simplified version of the hydrostatic pressure equation, which is just pressure at some point is equal to the ambient pressure plus rho gh, where h is a distance down from the surface, from the free surface that we're examining. And we have a corollary of that equation, which is dp dx is equal to 0, meaning that pressure hydrostatically does not vary with x according to this equation. So if we look at the first part of the manometer, where we're looking at pipe A and then we're going down to level A, we'll see that our height is h1 as shown in the diagram. Gravity is downwards and z is positive upwards. So what we can say then is P at little a is equal to P at big A plus rho H2O GH1. The way we get that is we know that our pressure is always going to increase as we go down in the direction of gravity. So the pressure at A is then larger than the pressure at big A in the pipe. And that has to be the case because the pressure down here has to be larger to support the weight of the fluid if this is going to be in static equilibrium. So pressure always increases in the direction of gravity. So pressure here at little a is equal to pressure at big A, or pressure in the pipe, plus the density of the water in the tube times G times H1. So P of little a is equal to P of big A plus rho H2O GH1. If we then look at the second part of the manometer, which is this part right here, connected to this first part that we looked at, then we'll see that we have a new height H2. When we look at a continuous run of the same fluid in static equilibrium, then we know that the pressure at a given level is always equal. So if we extend a horizontal line of A out in the fluid like this, then we know that the pressure here is equal to the pressure here because this is a continuous run of the same fluid in static equilibrium. So the pressure at this level, again, is equal to the pressure at this level because this is a horizontal line. And so we know then that A is lower than B according to this coordinate system. So we could say the pressure at A is equal to the pressure at B plus essentially the weight of this fluid. So plus rho Hg times G times H2. Where now we're looking at the mercury, so we're looking at the density of the mercury rather than the density of water as we had at the first section of this manometer. So now that we're looking at the mercury, this is going to be rho Hg. Now what we'll notice is we have two equations for P little a. So these two expressions are equal to one another, which is what this expression up here represents. Now, if we solve this for P big A, then we get this expression right here where we have P of little b plus rho HgGH2 minus rho H2OGH1. And that's just from setting these expressions equal to one another, which is just the hydrostatic pressure equation applied to the first section of this manometer and the hydrostatic pressure equation applied to the second section of this manometer. So we're going to apply the hydrostatic pressure equation in sequence across every section of this manometer and then combine the equations such that when we have PA and PB in the same expression, we can find delta P. So in the next section, we're looking at the third section of our manometer, which is this section right here, the oil. So again, remembering that the pressure at a given elevation within a continuous run of the same fluid is always equal, then if we extend out this line B horizontally at the same elevation, we know that the pressure here in this continuous run of oil is equal to the pressure here in this continuous run of oil. So the pressure here is equal to the pressure here. Here we see that C is lower than B, so we know the pressure at C is larger than the pressure at B because gravity is going downwards, and again, pressure always increases in the direction of gravity with this equation. So PC is greater than PB, so we can write PC is equal to PB plus the weight of this fluid column, which is rho oil times G times H3, which is the height between these 2 points. So we know from the first slide that PA is equal to this expression right here, which is just what we saw for when we set these 2 expressions equal to one another. And we know that that is a function of PB. Well, we just solved for PB in this third section of the manometer, so we just plug this expression right in here, and we get a new expression for PA, which is in terms of PC. And you can kind of see that what we're doing is we're starting with the pressure here, and we're expressing that in terms of A, and then in terms of B, and then in terms of C, and then in terms of D, and then we're going to finally get it in terms of B, and then we have PA and PB in the same expression, and that's how we can find the difference between pressures at A and pressures at B. So once we get our expression for PB and we plug it into the expression we got in the previous slide, we get this expression right here, which is the pressure of A as a function of the pressure at the free surface C. Now we hope to express PA in terms of PD. So we do that by looking at the fourth section of this manometer, 1, 2, 3, 4. And by applying the hydrostatic pressure equation to that, we can see that at this run of mercury, that if we extend our level C out, again, remembering the rule, PC is greater than PD. So what we could say then is PC is equal to PD plus the weight of this fluid column, which is mercury. So PC is equal to PD plus rho HgGH4, H4 being the distance between those 2 points. We see that our expression up here, PA, is in terms of PC. Well, we just found a new expression for PC. We could plug that into this expression, and we get PA is now a function of PD. We're almost finished. We just need to get PA as a function of PB. So what we're going to do is look at the final section of the manometer, which is the last water section, and that is this section right here. And you'll note that each diagram reminds us that gravity is down and Z is positive up, and that our pressure is always increasing in the direction of gravity. So we could draw out, again, that we have, let's do this in orange, that the pressure right here at this point is equal to the pressure at B. And that's because dP dx is 0, or the pressure change along the axis that is parallel to the free surface is always equal to 0. So these 2 pressures right here are the same. So what we can then say is PD is equal to the pressure right here, or pressure at capital B, plus the weight of this vertical fluid column, which is rho H2O G H5, where H5 is the elevation difference between B and D. Okay, so that's just to clarify that one section of the manometer right there. So with that in mind, we can write that PD is equal to P capital B plus rho H2O G H5. And you'll know from the last slide, we had PA as a function of PD, but now we have PD as a function of PB, so we can write PA as a function of PB. We then plug that in to this expression from the previous slide, which is the pressure at A as a function of the pressure at D, and then we finally have a pressure equation for the pressure at A as a function of the pressure at B. And what you'll notice is we have 1, 2, 3, 4, 5 terms in this expression, and each of these terms corresponds to a separate section within the manometer. So if you go to the original manometer, you'll see that we have 1, 2, 3, 4, 5 sections of the manometer, and we have our 5 expressions in the final equation that describe the pressure difference between these 2 points. So we have 5 sections of the manometer between those 2 points. So we have 5 terms in the equation that describes the pressure difference between those 2 points. So now all we're doing is plugging in all of these values into this equation right up here, and this is the final result. So a couple of things to note about this is you'll see that we're dividing by 39.37, and that approximately is just a conversion factor between inches and meters. So dividing some value in inches by 39.37 gets you approximately that value in meters. And our specific gravities here, so for example, 13.6, 0.9, we just multiply those values by the density of water at 4 degrees C to get the density of the fluid that we're examining. So in this case, we take 13.6 and multiply it by 1,000 and we get the density of mercury. And we take 0.9 and multiply by 1,000 and get the density of oil. And obviously these specific gravities are going to be functions of temperature and pressure depending on the fluid that you're examining. But those were given, so we're just going to use them as given. And when we plug in all of those values into our equation, we get 4,263.7 pascals. If we then divide that by 6,895, we can get that value in psi, and we'll see that the delta P between our water in pipe A and pipe B is approximately 0.62 psi. So the static pressure difference between the water in pipe A and the water in pipe B is approximately 0.6 of a psi. So you can see that this value will change as a function of the specific gravity of the fluids that you're using, your magnitude of gravitational acceleration. So this value will be different on Earth than it will be on the moon, than it will be on Jupiter, than it will be on anything else with a different gravitational field. And these heights will change depending on the pressures in the pipes that the manometer is between. So there's actually a shortcut for getting to this equation that doesn't require you to apply the hydrostatic pressure equation to each section of the manometer. If you're doing a more formal analysis, I would actually recommend that you do apply the hydrostatic pressure equation to each section of the manometer manually to ensure that you really understand why each section is doing what it's doing. However, if you're in a crunch for time, for example, you're in an exam, maybe the FE exam, maybe some other kind of exam, and you don't really have the time to manually apply the hydrostatic pressure equation to each section of the manometer, there is a shortcut, and that shortcut is as shown on the next slide. So if we look at the manometer as originally drawn, the shortcut is actually as shown here. And I'll just try to go over this fairly quickly, but we will be using this in future compound manometer problems. I just wanted to make sure that we had a video, a problem where we worked out the math manually, but future videos will probably use this equation right here just for ease of use. So looking at our shortcut, delta PAB, what we want to do is go from our point at A and work our way along the manometer until we get to the pressure at B. So using this equation, we have that the delta P between A and B is equal to G, as shown here, times the sum, which is represented by these brackets, of the rho I ZI's. So if we're starting at A and working our way along the manometer to B, A to B, then we say, okay, well, if I'm going from P big A to P little a, I know that my pressure is increasing. My pressure at little a is greater than my pressure at big A. So since my pressure is increasing, my ZI is negative. So then I say, okay, this is water, so what I have then is negative rho H2O times H1. Okay, now I look at the second section of my manometer towards B. I go from little a to little b. Well, in this case, my pressure is decreasing because my pressure here is smaller than my pressure here. So since my pressure is decreasing, my ZI is positive. So I would make this positive rho Hg times H2. Positive rho Hg times H2. Looking at this third section, the oil section, I'm going from B to C, and I know that PC is greater than PB because C is lower than B. So since my pressure is increasing, my ZI is negative, so then I could say that this is equal to negative rho oil times H3. Negative rho oil times H3. Now I'm going from C to D. I know that my pressure is decreasing because PC is greater than PD. So since my pressure is decreasing, my ZI is positive. So I can say that this is positive rho Hg times H4, positive rho Hg times H4. And then I'm going from D to B. And I know again that my pressure is decreasing because my pressure at D is greater than my pressure at B. So since my pressure is decreasing, I see that I have a positive ZI. So this is plus rho H2O H5. Now I'm at point B and my sum is complete. So this is the final expression that we get, and distributing the G to each term, you get this equation right here. Now if you compare this equation right here, which we get using the shortcut, which is just a copy and paste of this right here. So if we look at this equation here using the shortcut and we compare it to the equation that we get by applying the hydrostatic pressure equation manually, which is this equation right here, you'll see that they are exactly the same. So these terms are all the same. So whether you use the shortcut or the manual approach, it should give you the same result if they are applied correctly. Okay, so that should be it for this video. I very much appreciate you watching. Thank you very much, and I will see you next time.